Hello guys, my name is IBM. This is supposed to be part 2 of the question paper 5.1. I always don't like breaking this into two, but I had to change the font of the paper so that the graph can fit on the same page. So this was question 2, which is called analysis. We had already found the gradient, the expression for the gradient, and we had already found the expression for the y-intercept. In part 1, we calculated the values of v, we calculated the values of 1 over f, we calculated the uncertainties, and our task was to go to the graph. So let's plot the graph. I have the values written, so I wanted this graph to fit on the same page. That's why my device, that's how my device stopped working. Okay, so I have the values written on paper, so I'm just going to plot these points very carefully. First of all, you should establish the scale on the x-axis and on the y-axis. On the x-axis, one small square represents, I think it is representing 0.2. And on the vertical axis, one smaller square is representing, I think it's representing 0.5 times 10 to the power of minus 3, I think, or 5 times 10 to the power of minus 4. Okay, let's plot the first point from my table is 3.5 on the x-axis. 3.5 on the x-axis against 1.18. So 3.5 on the x-axis, 3.5 minus 3 divided by the scale, which is 0.2. So I'm going to add 2.5 squares on the x-axis. Then on the y-axis, I'm going to plot 1.118, 1.118 minus, because 1.118 is after 1.115, so I'll say minus 1.115 divided by the scale, which is 0.5. So I'll just add 6. I think there are 6 small squares. Maybe let me repeat this again. The scale on the x-axis is each small square represents, actually each small square represents, let me check the scale again, 1.075 minus 1.070 divided by 10. So each small square is 5 times 10 to the power of minus 4. So I'm trying to plot 1.118 minus the nearest point below it is 1.115 divided by the scale, which is 5 exponent minus 4. So I'm going to add 6 squares on 1.115. So 2.5 squares on the x-axis and then 6 squares on the y-axis. So this is going to be the point here. So the point is going to be 1, 2, 3, 2.5 on the x-axis and then 6 on the y-axis. So this is going to be the point in the middle of this box. So the plotting style is going to be an X and a small circle around the X. So do not do something like this. Just a small X and a circle. So I'll have to rub this and make it look extremely neat. 2, 5, 6. Okay. The next point is 6.3. So 6.3, I'll add, remember each small square is 0.2. So 1, 2, 3, 4, 5, that is 6. 6.2, 6.3 is in the middle of the box, I think. Then 110 is there. So we have 6.2.3110 is this point here. So that is the point. This is 6.2.3 is in the middle of the box. Okay. The next point is 8.7. So this is 8.2.4.6.7 is in the middle of the box. 8.7 is plotted against 1.101. 1.101. So this is 1.100. So how many boxes will I add to get 1.101? So I have to check this. So 1.101 minus 1.1 divided by the scale on the vertical, which is 5 exponent minus 4. So I'll just add two boxes to reach 1.101. So the point is going to be 1, 2. I think this is the point. Then the next one is 11.4. 11.4. So this is 11.2.4 is here. 11.4 is plotted against 1.092. 1.092 is after 1.09. So I'll say, using my calculator, I'll just say 1.092 minus the nearest point below is 1.09 divided by the scale, which is 5 exponent minus 4. So I'll add 4 points on, 4 boxes on 1.090. So 1, 2, 3, 4. So that is the point. Then the next point is 13.9. 13.9. This is 13.2.4.6.8. This is 14. So 0.9 is in between here. 13.9 is plotted against 1.083. 0.83 is after 0.80. So I'll use my calculator to see the number of boxes I'll add. So we have 1.083 minus 1.08 divided by the scale, which is 5 exponent minus 4. So I'm going to add 6 boxes on 1.08 to reach 1.083. So this is going to be 1, 2, 3, 4, 5, 6. So this is going to be the point in the middle of the box. The next is, the last one is 16.2. This is 16.2 is here. I'm going to plot that against 1.070, 1.074. 1.074, I'll use my calculator to see how many boxes. 1.074 minus 1.07 divided by the scale, which scale is 5 exponent minus 4. So I'm going to add 8 boxes. So 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be the point. Okay, I've tried my level best to plot all the points, and I'm now going to make sure that the graph fits on the same page so that I can easily judge the line of best fit. Okay, so I'll draw the line of best fit. In an exam, you can use a pencil for the line of best fit and use a pen maybe for the line of worst fit. So remember to try and balance the plotted points. I may not be very good at balancing because I'm doing this on a what? I'm trying to do this on a computer, so it's very hard to judge, to make a judgment. But remember to balance your points. So when I look at this line, I think this is not the best. Let me change this. The biggest problem with this application is that the eraser erases everything. So I have to replot again. 16.2 towards this point here. Sometimes when you notice that the line of best fit is not coming out very well, try to cross-check again the plotted points. I think the second point, I need to check the second point again. The second point was I think it is correct. So let me try an attempt. I'm just going to use one attempt. After my role is to just give you a hint on how to do this work. On paper, it is easy to make judgment, but on computer, it is really very hard to make judgment for the line of best fit. But the major point is that the points should be well balanced above and below the line. So I'm going to take this one as my line of best fit. Okay, I'm just going to take this one. I will not be able to draw a better line of best fit because every time I repeat, I'm wasting time. However, I tried to aim at making sure that this point is on the line. This point is very close to the line. This one is in the line. This one is in the line, and I was aiming at leaving 1 point above and 1 point below the line so that the points are balanced. But I couldn't do that very well on a computer, so try to draw a better line of best fit. Let me try to reduce the size of the eraser. This point was 11.4, which is this point here. 11.4 was against 2, which was 1, 2, 3, 4. Okay, so you can draw a better line of best fit. Me, I've just given you a hint. Okay, then the next thing is I'm just going to draw the error bars. Remember, my graph is not final. You could have a better graph. You could make proper judgment. The aim is to ensure that the points are well balanced above and below the line. So I try to assume that these 1, 2, 3, 4 points on the line, and it leaves one below and one above. You can try to, if you plot carefully, I think that's most likely what you're going to get. So let me draw the error bars. I'll draw the error bars. I'll increase the thickness slightly, and I may change the color just to make them visible. For learning purposes, you don't need to change the color in the exam. So in the exam, you may use, okay, let me use green for the error bars. The error bars are going to be horizontal. The first error bar was 0.4. Remember the x-axis, each small square is 0.2, so 0.4, those are two small squares. So I'll have two small squares on both sides. And remember this was in the center, so two small squares, it means half, 1.5, half, 1.5. So it is going to be somewhere here. It is in the middle of the box because this point was in the center. So it is going to be in the middle of the box. Then the second one is 0.4 also. This was also in the middle of the box. So half plus 1 plus a half, it is going to be in the middle of the box. This is stressing. A half, 1.5. So that is in the middle of the box, this side, and in the middle of the box, the other side. So try to make the error bar a little bit bold and visible. Use a ruler for your error bar. I may use a free hand because it is on a computer. Then the next one was 0.5. This point was also in the middle of the box. So we have a half, 1, 2. That is 0.5 because two small squares 0.4, then plus a half. So this will be somewhere here. Then a half on the left, 1, 2. That is 0.5 this side. Then we join the error bar. We join the bars. Something like that. Then the next one is exactly at the grid line. So 0.5, it will stop in the center of the box. 1, 2.5. So this will be somewhere here. One, 2.5, somewhere here in the middle of the box. Then 1, 2.5, somewhere here in the middle of the box. Then you join the error bars. Make sure the error bars are in the middle of the box. Mine is just thick because I'm drawing on a computer. Then we have the next one is 0.6. Those are 3 to the left, 3 to the right. But because the point was in the center, so two small squares 0.4, then I will add half. So this is going to be the point in the center of the box. Then I also do the same on the other side. One, 2.5. So this is in the center of the box. Then I will join the bars. Please use a ruler for the error bars. And then last one was also 0.6, but was exactly at the grid where the grid lines are crossing. So I'll just count 1, 2, 3 to the right. 1, 2, 3 to the right, and 1, 2, 3 to the left. That is 0.6. Then I'll join these ones. So those will be the error bars. So I'll try to fit this on the same page. Okay. So the next thing I'm going to do is to make a judgment for the line of worst fit. So for the line of worst fit, I can first of all check by joining the top of the top error bar to the bottom of the bottom error bar and see if all the error bars are crossed. If they are not, I will not draw that line. All the error bars must be crossed. So if I join the top, or if I join the left of the top error bar to the right of the bottom error bar, I see that the second error bar from the top is not crossed. So I will not take that method. I'll try to join the right hand side of the top error bar and the left hand side of the bottom error bar. And when I do that, it appears as if all the error bars are almost crossed, but one of them may be left out. So I have to adjust my line to ensure that all the error bars are crossed. So I'll draw my line of worst fit like this. It may not be absolute because this is using on a computer, so the error bars boundaries may not be as good as it would be if you were to draw on paper. However, the rule is all the error bars must be crossed. So all the error bars must be crossed. So you can see my line is crossing all the error bars. The least point is at this point here. That's how we can conclude that all the error bars have been crossed. So this line shows all the error bars have been crossed. I was aiming at crossing through this point here. Okay. The next thing is to draw the triangles for the gradient. So I may draw one triangle for both lines. So I want to draw one triangle for both lines. Let me use a color which is visible to people but different. Let me use red for that the triangle. So when choosing the points for the triangle, make sure that those are the points where the grid lines perfectly cross perfectly cross each other. For example, when you look at this point and this point, the grid lines perfectly cross each other. Then up here, I have this line, that point, and I'm trying to look for points where the grid lines perfectly cross. Even though the line is not perfect, I may take these 2 points. No, I need them in the vertical, sorry. In the vertical, okay, I'll take this point and this one. Remember, these points are not absolute because this is on a computer. The line is not perfectly straight. So you must be very careful. This is just a guide. So now I'm drawing the triangle. The precision of the pen is not very good. That's why you see I'm not drawing exactly on the line. Yeah, but at least I've made it better. Then down here on the x-axis, okay, so this is our triangle for finding the gradient. One triangle is enough for both lines. If it is not possible to draw one triangle, then you can draw more than one. You can draw 2 triangles to help you find the gradient. But they said label the lines, so I have to label these lines. Remember to label your lines. This is the green one is the line of worst fit. The blue one is the line of best fit. Then I'm now just going to write the values from the table, from the graph that I'll use for the gradient. I'll start with the blue line where I'll record its values, the x values. Let me record them on paper. So I'm reading this point here. Remember, you should have the scale at the back of your mind. So on the x-axis, this is 15.2, 0.4, 0.6, 0.8. So this is 15.6. So that is 15.6. Then on the x-axis again, this point here. So this is 14 point, I think that is 14.2. This is 14.2. So 15.6 minus 14.2 on the x-axis. Then on the y-axis, this value is 1, 2, 3, 4, 5. 5 times 5 exponent minus 5. So that is going to be 1.075 plus 5 boxes times 5 exponent minus 4. So that is 1.077. This is 1.0775. Then the top here, we are reading this point here, which is this one. There are 2 boxes, so I'll use my calculator. I'm going to add 1.15 plus, there are 2 boxes times the scale, which is 5 exponent minus 4. So that is 1.116. Sorry. So it's 1.116. Yeah. Let me also read the values for the green line so that I just calculate at once. So we also have this one here for the green line, which is 1.115 plus, open brackets, how many boxes? 1, 2, 3, 4. So there are 4 times the scale, which is 5 exponent minus 4. So it becomes 1.117. 1.117. Okay. Let me also read the x value for green this side. Of course, for green this side is just 15. So let me just now. So now I have values for this one. I have 15.0, and on the x-axis I have 1.0775. 1.0775. Don't forget this is times 10 to the power of minus 3. Then here I have 15.6 against the same x value 1.0775. Of course, this is times 10 to the power of minus 3. Then I also have the values here. So this is supposed to be 1.0775 minus 1.116. This is 0.0775 minus 1.117. Yeah, these are supposed to be negative values because the line is having a negative gradient. So So this is 4, not 14. I don't know where I got 4 from. So this is 4.2. So I have to start with 1.0775 minus 1.117. Then I have 1.0775 minus 1.116. Then on the x-axis I have 15.6 minus 4.2 and then 15.0 minus 4.2. Okay, sorry about this. I have to check this again. Sorry about that. So 1.0775 minus 1.116 divided by 15.6 minus 4.2, then times 1 exponent minus 3. So it's negative 3.38 times 10 to the power of minus 6. Negative 3.38 times 10 to the power of minus 6. Then this one is going to be 1.0775 minus 1.117 divided by 15 minus 4.2 times 1 exponent minus 3. So this is a minus 3.66 times 10 to the power of minus 6. Minus 3.66 times 10 to the power of minus 6. So I have to change this. So the uncertainty is going to be, I'll just say 3.66 minus 3.38 times 10 to the power of minus 6 after it is plus or minus. So 3.66 minus 3.38, that is 0.28 times 10 to the power of minus 6. 0.28 times 10 to the power of minus 6. So here I will just write my answer as negative 3.38 plus or minus 0.28 times 10 to the power of minus 6. Okay. So I think that is going to be correct, or it makes sense. You may get a different value depending on how accurate you could be. Then determine the y-intercept of the line of best fit. Include the absolute uncertainty in your answer. So for the y-intercept, of course, we have to use the equation y equals to mx plus c. So I'll find c for the best fit, which is going to be, I'll just take the values for the gradient that I used. I just take one pair. For the best fit, I had 15.6 and 1.075775 times 10 to the power of minus 3. And then for the worst fit, I'll just take 15.0 and 1.0775 times 10 to the power of minus 3. I just need a point from the graph, from the line. So for the best fit, the y value I'm taking is 1.0775 times 10 to the power of minus 3. That is the y value, minus the gradient for best fit, which is negative 3.38 times 10 to the power of minus 6. The x value I've taken is 15.6. So that is the C for best fit. Then C for the worst fit. The y value I'm taking is 1.0775 times 10 to the power of minus 3. Then minus the gradient for best fit is minus 3.66 times 10 to the power of minus 6. Then times the x value, which I'm taking is 15.0. So I'll just check my calculator. So I'll start with the 1.0775 exponent minus 3, then minus, open brackets, negative. I'll start with what is outside, 15.6 times 3.38 exponent minus 6. So I'm getting 1.13 times 10 to the power of minus 3. 1.13 times 10 to the power of minus 3. Then for the worst fit, I have 1.0775 exponent minus 3 minus, open brackets. I will start with 15 times negative 3.66 exponent minus 6. So I'm getting 1.1. Okay, this is 1.132. I'm going to add in one significant figure on the previous one because an uncertainty of 0 is not going to be accepted. So I have to check the previous one. 1.0775 exponent minus 3 minus 15.6 times negative 3.38 exponent minus 6. What have I done? 1.0775 exponent minus 3, then minus negative 15.6 times 3.38 exponent minus 6. So it's 1.130. 1.130. Okay. So the uncertainty is going to be 1.132 minus 1.130 times 10 to the power of minus 3, which is 1.132 minus 1.130. So this is 2 times 10 to the power of minus 3. So it becomes 2 times 10 to the power of minus 6, or it becomes 0.002 times 10 to the power of minus 3. So the uncertainty here is the y-intercept here is going to be 1.130 plus or minus 0.002. Then this is times 10 to the power of minus 3. Okay. Then using your answers to A, C, Roman 2, Roman 4, determine the values of Fs and K, include the appropriate units. Of course, from part A of this question, we saw that Fs, or the y-intercept, was equal to 1 over Fs, which means Fs is equal to 1 divided by the y-intercept. So this is going to be 1 divided by the y-intercept, which is 1.130 0 times 10 to the power of minus 3. Then we're determining fs and k. Then for k, remember the gradient, k was equal to, the gradient was equal to -1 over gradient. The gradient was equal to -1 over kfs from question 1. So k is equal to -1 over the gradient times fs. So let me press the calculator here first. 1 divided by 1.13 exponent minus 3. So that is 885. 885. So this is going to be a negative of 1 over the gradient. The gradient was negative, I think, 3.38 times 10 to the power of minus 6. Then times fs, which is 885. So the answer 885 times, of course the negative is cancelling, so I will just say times 3.38 exponent minus 6. Then I will say 1 divided by the answer. So that is 334. So this is 334. It becomes positive. Now let's check the units. So y-intercept on the y-axis, what are the units? On the y-axis we have hertz power minus 1. So the y-intercept, hertz power minus 1. So you have 1 divided by hertz power minus 1, which is going to be equal to hertz. So fs is going to be in hertz. Then for k is going to be equal to 1 over, then for fs is hertz. Then for gradient is hertz power minus 1 divided by v meters per second. So divide by meters per second. Remember, hertz is the same as per second. So meters per second, and then per second, this one cancels with that one, I think. So it becomes meters hertz, I think. But remember, hertz is the same as, sorry, this one, hertz and per hertz. We have hertz per hertz times hertz. Okay, this one has already cancelled, so it becomes per meter, sorry, meters per second. So this is meters per second. I can try to show this again. The units for k, I'm deriving the units for k. It is 1 over gradient is hertz per -1 divided by velocity speed, which is meters per second, then times fs, which is hertz. So per hertz and hertz, this one cancels out, then this one goes up. So it becomes meters per second. Okay, so I think these answers are going to be correct. And then determine the percentage uncertainty in K. Since we have the absolute uncertainty in we have the absolute in the gradient, but it is easier to find the uncertainty in K using let me go back to the first equation. So the gradient, when I look at K here, gradient equals to -1 over K times Fs, which is that is -1 over K times 1 over fs, and 1 over fs is the y-intercept, so the gradient is equal to negative 1 over k times the y-intercept. Since I have the uncertainty for the y-intercept and the uncertainty for the gradient, then I'm going to use that formula, because k is going to be equal to negative of the y-intercept divided by the gradient. It becomes easier to do it that way. Or I would find k for the best fit, k for the worst fit, and then I subtract. But I will use this one here. So k is equal to the negative of the y-intercept divided by the gradient. So it means the percentage uncertainty in k is going to be equal to the percentage in the y-intercept, which is going to be 0.002 divided by 1.130 times, of course, 100, plus for the gradient it was 0.28 over 3.38. I'm ignoring the power of 10 because it will cancel out. So it is 0.28 divided by 3.38. Then I'll multiply this by 100. So I have that 0.002 divided by 1.13 plus 0.28 divided by 3.38, then times 100. So that is 8.5%. Like I say, these answers are not absolute. Your answers could be slightly different. I'm interested in the method. Then the experiment is repeated. Determine the speed v that gives a value of 987.8 hertz. So of course, we saw from the first equation, when I make v the subject, I think if I make v the subject, let me first go back to the equation. If you make v the subject, cross multiplying, you'll see that v is going to be equal to, I think it will be k minus kfs divided by f. I have k, I have fs, and they have given me f, so I can just substitute. Okay, so v equals to k minus kfs divided by f. So I'm substituting. K is 334 minus 334 times fs, which is 885 divided by 987.8. Okay, so I have 334 times 885 divided by 987.8. Then I'll say 334 minus the answer. So V is going to be 34. 34.8 meters per second. Alternatively, you could find V from V equals to, V could be equal to 1 over F minus, I think it could be minus the y-intercept, divided by the gradient. Because if K equals to the y-intercept minus y-intercept over gradient, and yet V equals to K minus KFS over F, then it means V can be equal to 1 over F minus the y-intercept divided by the gradient. You would get also an acceptable answer. Yeah, it is not really very easy to solve question number 2 of paper 5, but at least I try my level best to give you a hint. If there are errors, you are going to forgive me. I will not edit it. I have not edited this video because I want you to see the errors that are most likely going to be made during the exam. So until next time, bye bye.